let's start the first lecture on numerical optimization. Okay, so firstly, why we want to learn numerical optimization? Okay, but to answer this one, actually the first thing we want to answer is why we have models or why we build models. Okay, in the past, actually until today, we build a lot of models. Okay, many kind of models. Okay, and this kind of models is to help us to understand or to explain or to predict many things like natural phenomena, like the biological systems, like the business profit or loss, or even the disease outbreak. Okay, of course, all this, especially you see this one and this one, or this one. Okay, a bit different. This one basically is about numbers. Okay, but all this, okay, can be something not related to numbers as well, right? For example, biological system. Where can you see numbers in biological cells or whatever, right? So we don't have number here, but we try to build models, okay, which based on mathematics, okay, so that we can explain all these things in a numerical way, So this is the beginning of it. Okay, we need models to understand a lot of things, okay, in a systematical way. So when I say systematical way, when we say we want to predict something, means there's, okay, no way we can escape from mathematics, right? So all these models that I mentioned just now actually can be written. Most of them can be written in the form of a mathematical function. Okay, a function is actually it's just a equation with a lot of variables that we know or are unknown. Okay, and then with these variables we compute something. This is what we call function. Okay, function is very powerful today. Even the deep learning that maybe a lot of you have learned it, or machine learning or whatever. Okay, all this deep learning, for example CNN, whatever. Okay, they are what is the CNN? There's nothing but just a set of functions, right? Deep learning, or what call it, CNN, or whatever it is, again. Okay, actually there's just set of functions that works to help us to predict something, right? So all these models, okay, actually can be written in the form of mathematical functions. And with the function, we know we have a lot of parameters in the function, right? So what we want, okay, we want to find the best set of parameters in the function, so that we can do a lot of things. For example, we can model the system precisely. We can perform very accurate prediction. Or if we are going to use it to model the business, okay, then it can help us to reduce the cost running the business, maybe. Or it can help us to maximize the revenue, or it can increase the efficiency or the stability. Okay, so this is many things, okay, we can do with models. We convert one physical system to models. Okay, we can do a lot of things to find these parameters. Okay, the best set of parameters. How to find it? Okay, there are two ways. First, guess. Okay, just sort of try and error. Okay, you get a parameter. Okay, it works or not. It doesn't work, then we change to the new set. Okay, by luck. Okay, or try and error. Okay, the other method is using what we are going to learn is so-called the numerical optimization. Numerical optimization is a mathematical way, is a scientific way to find, okay, the set of parameters that we want, that can help us to do the prediction, or to reduce the cost and so on. Okay, so this is the methods. So we won't talk about this one. Okay, we will focus on this part only. Okay, before we continue with more about the numerical optimization, there are some terms that we want to learn first. First is model. Okay, model, as I mentioned just now, is mathematics concept. Okay, we actually it's a description of a system. Okay, it's a physical system or virtual system using mathematical concepts in language. Means we develop them. Okay, we find what is working or what's affecting the output of the system. Okay, what's output affecting the output of the system, we quantify it. Okay, we quantify it and we make it become a set of mathematical equations or functions. So this is so-called a model. Okay, and the modeling is the process of developing the models, in which include the identifying of the variables, identifying the objective, and the constraints of the problems. Okay, and the third one is variables. What's variable? I have mentioned variable just now. Variable actually means that the characteristic of systems that can affect the performance of the system. For example, in the business system, maybe the variables include the manpower, how many manpower we have, the quality or the quantity of the materials. All these are variables. Okay, constraints, the limit, the restriction of the variables. For example, in some cases, we have restriction of on variables. For example, let's say we are talking about manpower. The manpower surely is a number which is greater than zero, right? Greater than zero, and it's a integer. Okay. Is there any upper limit? Zero is a lower limit. Upper limit. Okay, that depends on the another variable. The the funding of the company, right? So then when the funding is coming in, you find another constraint as well, right? So constraint is the restriction of the variables. And objective, okay, objective is what we know. When we talk about objective is what we want to achieve, right? So but here when we talk about objective, actually it's a quantitative measure of the performance of the system under study. Means that with the variables we know, we can measure, okay, how is the performance of the system. Okay, so most of the time we relate the objective to a function. We call it objective function. Sometimes we call it as cost function or loss functions. Okay, loss function or cost function or objective function. Okay, actually they mean the same thing. Is what we want to achieve when the system is at the optimal condition. Okay, maybe most of the time, in many cases, we want to make it become maximum or minimum. Okay, for example, when we what I mean is, for example, when we say we are modeling business systems, okay, then the objective function, okay, could be the revenue of the system, okay, of the business model. Then, what we want, we most of the time we want to make maximum profit, right? So the objective function, we want to find the maximum of it. Okay, but for some cases, for example, in many machine learning algorithms, when we talk about the machine learning algorithms, we want to have lowest error. Okay, we want to have lowest error. So to have lowest error, what we want, we want to we want the objective function or the cost function to be minimum, because the cost function or objective function refers to the error. Okay, most of the time it refers to error of the system. So this one, okay, okay, optimization. Okay, we have a system that work in real life. Let's say, okay, so to make the system uh, work perfectly, we need to determine the parameters inside the system, the number of staff for this business system, for example, and then what are the materials we need, okay, quantity, quality, okay, so that the system work in a perfect way. So to find these numbers, to find these variables, okay, the process is called the optimization, and the goal is to find the best set of this value. So in fact, for this process we have two steps. Step one, we build model, okay, build a mathematical model that uh, represents how this system work, okay, and then of course, I mean, how this system works, it means that how all these parameters interact with each other, how these value parameters interacts, okay. So and how the value, I mean the output, okay, can be reflected by the change of the parameters, okay. And the second step, we use an optimization algorithms, a mathematical way to find this set of parameters, the best parameter we can have for this system to work. So here, when I say find an optimization algorithm, that means we have many optimization algorithms, but we just want to choose one that will help us to solve the problem. Okay, there are many algorithms out there. Okay, but no one work universally. That means some of these algorithms work well in some system or some problems, but they are not in some other problems. Okay, so why? Okay, maybe sometimes we ask why, this common, why we don't have one algorithm that can solve all the problems, because all the algorithms are problem dependent. Okay, which one to use depends on what kind of problems. This is easy to understand because even in our real life, okay, there's no medicine that can cure all the diseases, right? No medicine that can cure all diseases. Just similarly, no algorithms can solve all the problems, right? So this one is the, okay. Let's look at some detail of this optimization. Okay, uh, as I mentioned just now, a system can be modeled to become a function. Okay, function. Okay, function with parameters x. Okay, x can be a vector, so that you actually have many variables inside here. So we want to find the minimum, okay, of this function. Means we want to optimize it. Okay, so this, okay, so x here is the variables and f is the objective function. Okay, you want to find the minimum of objective function, means that you want to find the, for example, in machine learning, if let's say this is machine learning, then you want to find the variables that create less errors compared to others. Okay, but for some situations, beside the function, beside the objective function, we also have a list of constraints. A list of constraints means that for some variables we must have it equal to 0, or for some other parameters we want to have it greater or equal to 0. Okay, these are so called the equality or inequalities. All these are constraints to the system. Okay, constraint not to the function, not to the object function, but constraint to the systems that we are studying. Okay, so the object function is just the other equation that showing how the system works. Okay, so this is a, okay, three main components in the optimization. Okay, and one term that I want to introduce here is the so-called feasibility region. Feasibility region actually is a region where the variable there meet the um, meet the constraints, all the constraints. For example, let me, okay, here, this another example here. Okay, so you see, let's say this is an objective function. Okay, an objective function with two variables, s1 and s2. So if you plot, you see, you can see that actually this is a quadratic uh, expression, right? Quadratic expression. So for this objective function, actually you have the contour of the objective function start from here. Let's say, okay, the value will become lower, higher and higher when it's away from the middle point here. Okay, so I mean, what I mean is when s1 is 0, s1 is 2, okay, and s2 is 1. This is s1, s1 is 2, 1 here. Okay, so this s2 1, s1 2. Okay, so you see the value of this will become minimum 0. Okay, when it is further from this point, the value the value of the objective function become higher and higher. Okay, it's easy to see, right? Because when s1 is growing, s2 is growing, you have one larger number. Okay, and because it's a square, okay, it's become larger and larger. So when it's further than this point, the value become larger. Okay, this is objective functions. But in the case of we have constraints, okay, wait, if we do not have if we do not have constraints, okay, then to find the minimum value, okay, if you have this one only, minimum is very easy. We can see already it's here, 0. The value of the objective function is 0 here, and the s1 s2 we know already. Okay, but when we have constraints, okay, we need to study the constraint. Okay, for example, this is the first constraint, s1 square minus s2 less than or equal to 0, this curve. Okay, uh, so and okay, when I say this curve means that this is equal to 0. Okay, but when it's less than or equal to 0, okay, is the area, okay, on the top here. Okay, the next constraint, the red one, okay, the red one, s1 plus s2 is less than or equal to 2. This is this line. Okay, this line, when it's less than or equal to, you have the area here. Okay, this area. So we study it at one complete problems. Okay, means that we want to study all the constraints together. Okay, we must find the region that fulfill both constraints, which is the green one here. Okay, the intersection of both the red and blue one, the green one here. Okay, this is the part where both constraints are fulfilled. So this kind of regions, okay, which fulfill all the constraints, we call them as a feasible region. The feasible region is the region that fulfill all the constraints. Okay, now come back to the objective function. Objective functions I mentioned just now, we want to find the minimum. Okay, so to find when we want to find the minimum, we don't rely on the objective function only, but we want to look at the constraints. So you see, when the objective function is growing, become larger and larger, when it first meet the feasible region, this is a point. So this point give us the best value that fulfill all the constraints, and then we can find the minimum of the objective function. So this is what we are going to learn. This is just one example that we are of the problems that we are going to solve in the future. I repeat, this is just one example. Don't worry about this example, but I just want to give you some idea. Okay, this is just one of the example that reflecting the problems that we are going to solve in the future. Okay, but of course, at the beginning, we are going to focus on minimizing of this function only. What it means, we are going to focus on the unconstrained optimization only. Means we are going to have objective functions without constraints, and in the second part, we will bring in constraints to solve. Okay, so this is what we are. Okay, one more thing is, in many cases, we find minimum of objective function only. Okay, we are more interested in minimum of objective function only in many cases. This is very obvious, because for example, in our machine learning side, we want to minimize the cost function. We want to minimize the cost function so that the error of our model is lowest. Okay, because the cost functions means the error. Okay, means the error of the model, right? So we want to minimize it. Okay, but in some cases, we need to find the maximum. Most of the time, we find the minimum. Okay, but in some cases, we want to find the maximum. So we don't have a special algorithms to find the maximum one. Okay, for example, you want to find the profit of a company, you want to find the maximum, right? But we don't have a special special algorithms for the maximum one, but we always can convert one algorithms to which find the minimum to find the maximum easily. Okay, for example, if this one, the blue one, the red one, sorry, the red one is a function. Of course, this function we do not have a minimum, right? We do not have a minimum. We can't find a minimum here. But we are interested in the maximum. This point, we are interested in the maximum. So to solve the problem, to find the maximum of this function, okay, what we can do actually is very simple. We can use any algorithms that can find the minimum. Okay, what we do is this function fs, we find the negative of it. We find the negative f, or this negative. Okay, the is a mistake here. The negative should be here. Okay, we find the negative of this fs. The red one is the fs. The negative fs is the blue one. Okay, you see, once we convert it to negative, when we change it to negative, you see, this is a minimum, right? We can find the minimum of this function using the mean algorithms. Okay, the algorithm for means. Okay, and then we find the value of s. The variable, okay, must be the same. Okay, but then when you have the s, okay, you can just plug into here to find the minimum, or plug into here to find the maximum. So in short, we to find the maximum, okay, of a function, okay, we can use any algorithms for the minimization, okay, and we find the mean of the negative fs. Done. Okay. Okay. So there are many ways to find the. Of course, when I come to here, when I talk about minimum or maximum, some of you may already think of one way. You find a dy dx. Okay. And you go to 0. Okay, find dy dx to go to 0, then you can find the minimum or maximum, right? Yes, correct. You're right. Okay, but this kind of problem, this kind of solution, finding the derivative, we call it as a analytical way. Analytical way of solving problems. Okay, they are useful, they are powerful. Okay, but what we want to learn here is not this one. We want to learn so-called the numerical optimization, the numerical way. Okay, the numerical way is like this. It is iterative algorithms. Iterative algorithms means that it's a kind of algorithms that repeat steps again and again and again until you achieve the objective, until you get what you want. Okay, so it always start with some guess value, initial value. Okay, always start with some initial value and repeat the steps and stop when some stopping criteria is achieved. Okay, what I mean by stopping criteria here is some, for example, you reach the maximum iterations. Okay, you meet the maximum iterations. Okay, let's say you say I can afford to run 1,000 or 10,000 iterations only. So when this number achieved, okay, 10,000 iterations achieved, okay, you stop. Okay, or you can say the new iterations return the same value of s. Okay, the s is the variables. Okay, if you run again and again, you find that it always give you the same s, means that there's no more improvement, then you can stop. Okay, and then the third one is new iteration bring no or little change to the function value, the objective function or the cost function. Okay, the cost function, okay, no change at all or little change, then you can stop as well. So here I told you that numerical optimization is iterative algorithms, means we want to repeat the steps again and again until we reach the we find something, okay, we find something we want. Okay, this is totally different from the analytical way, where we can find the value, the the x, the variables, the optimal variables easily, right? Okay, why we need this method instead of this one? Because analytical methods is very good, okay, powerful, but the problem is sometimes it is not enough to solve, some complicated problems. For example, if you have problems with not only this kind of polynomial um, function, but you have sine 3x squared plus 2, okay, minus cos x ln x plus 5 uh, 5 square and so on. You see, when the function becomes so complicated, okay, this is only one variable, and you have, let's say you have more than one variables, and then it become more complicated, right? So analytical way is not able to solve when the function growth become too complicated. So what we can do is, okay, instead we work hard to solve it using analytical way, we use iterative methods, okay, to solve it, the numerical method to solve it. The numerical methods, okay, not only we have equations to solve, but since we need to repeat, okay, we need to repeat the computation again and again. So most of the time we will use computers, we write programs to solve it, okay, we use program to help us to solve the problems, okay, because we want to repeat counting something using the same equation but just different value, then program is the best way. Okay, so here we will learn a few types of optimizations. Okay, first one is the so-called continuous versus the discrete optimization. Okay, for the discrete optimization, okay, we have the variables, okay, I mean here if we have a function fs, these are variables, right? So the variables involved here are discrete. Okay, this, when I say discrete, they can be binary, or they can be integer, or they can be from a set, okay, a finite set of values. Okay, this is what we call the discrete optimizations. Okay, so if the s involved here, the s can be any real number, okay, then this is not discrete, this is a continuous optimizations, the variable that we deal with. Okay, we are not talking about the result of the function, but we are talking about the variable we deal with. Is the discrete one or the continuous one? S is real number, continuous. S is from the set of integer, a set of binary, or from a set, limited set of values, then that is the discrete optimization. Okay, so for the continuous optimization, okay, even though we are dealing with real numbers which can be any value from negative infinity to positive infinity, actually it's easier compared to the discrete one. Okay, constraint or unconstrained optimization, this one we discussed already just now. Okay, we have in some optimization problem we have a set of equality to fulfill, or in some other we have a set of inequality to fulfill. But when we have no equality and inequalities, this one we call it as a unconstrained optimization, okay, or this is an unconstrained problem. Okay, so to solve this kind of unconstrained problem, we can use unconstrained optimization algorithms such as line search methods, structural methods, and so on. Okay, if this is a constraint one, okay, we come with some constraints, then we can use methods like linear programming or non-linear programming. Okay, if what I mean here is if the function itself, and so the set of constraints are all linear functions, okay, no square, no higher power than 1, okay, then this is so-called the linear functions, then we can use linear programming. Otherwise we have to use the non-linear programming. Okay, and global versus local optimization. uh, some algorithms or some problems, okay, is easy, okay, because they have only one minimizers only. What I mean is, I draw here. Let's say this function, to find the minimum is easy because there's only one minimum point. Okay, maybe we can find easily, but for some problems, okay, I mean some functions, okay, which are very complicated, they have many minimum points. Okay, all these minimum points, we can consider them as a local minima. When I say local minima, means that this is a minimum point, okay, at the neighborhood. This is the minimum point at the neighborhood. Okay, no other point which is lower than this one in this neighborhood. Okay, so this is so-called the local minima. But there's one point, or maybe two, okay, which is the lowest for the whole value of the function. Okay, if this is the lowest one in the whole function, we call this as a global minimum, global minima. Okay, and to solve this, this is so-called the global optimization. We find the global minima. Okay, some cases we only can find the local minima. Okay, so local minima, when I say local minima, this one means that the local solution, okay, minima solution to this neighborhood. Okay, global solution means the best solution for the whole function. Okay, so it's not easy. It's not easy to find the global minima. Okay, because some functions, some simple one we still can find, but some very complicated function, okay, we can't even know how the function works in some extreme region, right? So it's not easy to find global minima in some cases. Okay, so for this course we will focus on global minima only. Yeah, there are some algorithms which is very good in finding global minimum, but this is not our focus here. This kind of problem, if you're interested, you can study so-called evolutionary computations. Okay, there are some algorithms in this category of algorithms which is very good in solving this kind of global minimization. Okay, stochastic and deterministic optimization. Deterministic means that we are working on the stochastic and deterministic optimizations. Okay, we talk about deterministic. Okay, what we mean here is we are talking about a system which the system can be completely specified. We know everything about it. For example, when we let's say a board game, like a chess. Okay, a chess, when we play a chess, okay, whatever possibility there, we can imagine, we can know. Okay, because they are all in the rules of game of the chess, right? So this is so-called a deterministic situation. No, I mean deterministic problems. Okay, there's no sort of unexpected thing there. Okay, everything is expected. Just we can imagine, we can expect it earlier before our opponent move it or not. Okay, so the other one is the so-called stochastic optimizations. Stochastic system is a system that deal with some uncertainty. Okay, there are something that we cannot predict. It comes with some randomness. For example, some economic systems, okay, or financial models. Okay, these are models that come with some uncertainty. We do know when will the next pandemic happen that will change the I mean the run of economics daily, right? So these are something that we cannot predict. Okay, there are many issue as well that we cannot predict in economy and financial models. So this kind of models we call it as stochastic models, and then we need stochastic optimization. Function, convex function. Okay, a convex function f, okay, a function f is a convex function if the function fulfill these inequalities. Okay, don't worry. What I mean here is one. wait okay, when we have a function, okay, uh, this function fulfill this inequality with any value of lambda, where the lambda is a value, okay, lambda is a value be between 0 and 1, okay. If this is fulfilled, that means, okay, this is fulfilled, that means this is a convex function. Or I draw it. What it means, if this function, you see, you choose any 2 points, let's say this is s1, this is s2, okay. If you connect the s1 to s2, this chord, okay, this is a chord, okay. If the value of the chord is always greater than this function, okay, you see this is a value of function, the value of chord is always greater or equal to the value of function, this is convex, okay. If in another case, okay, if you have this one, here is s1, you can pick, okay, s1 and s2 can be any 2 points, okay. This is s2, okay. You see, this is a chord. At this area, the value of chord is greater than the function, right? But here, no. The value of function is greater than the chord. So this is non-convex. Okay, so what is the big deal here? Why we don't want to learn convex or non-convex? If it's a convex function, if this is a convex function, okay, it's very easy. We always can find one minimizer, and this minimizer is a global one. Okay, so finding global minimizer for convex function is very easy, but in many cases we are dealing with non-convex one. Okay, means we have more than one minimizers. Okay, yeah, this one is repeated already. Okay, so yeah, one thing here. Okay, concave function. A concave function is the negative. Wait, maybe let's write this. This one. Okay, so this is a let's say this is a function, a convex one. Okay, fs, this is f convex. Okay, the negative of f, okay, you can imagine this is something like this, right? Okay, if this is a convex function, wait, about this one, okay, then this is concave. In short, concave function, you find the negative of it, you find the convex function. Okay, if one function, the negative of that function is a convex one, that means the function is concave. Okay, so we'll see some optimization algorithms in the future. Okay, there are many, but for good optimization problems, good optimization algorithms, okay, it should fulfill these 3 requirements. First is robust. That means it can perform well in a few kind of problems, not only one. Okay, it works well in some, at least some problems. Okay, and second is efficient. Efficient means that it does not require too high computing resources, okay, including time and storage to perform the work. And then thirdly, it must be accurate. Okay, accurate. So this is what we require for optimization algorithms. Okay, in the past, it is quite common that some students come and ask me, they said they still cannot understand why we need so-called numerical optimization. They don't even understand why we want to find minimum, okay, of a function. Okay, okay, actually, this is because I understand some students have not taken the machine learning class yet. Okay, anyway, I try to explain a bit on, okay, one of the example of numerical optimization as a solution to machine learning algorithms especially the linear regression. Okay, I mean here, numerical optimization can be solution for many things, including machine learning algorithms such as linear regression. Okay, here look at this example. Let's say we have a data of advertisement spending, okay, which we call S, and then we also have the data on the revenue after we spend so much on the advertisement. So we know the amount of advertisement we spend S is linearly proportional to the revenue Y. What I mean here is if S increase, Y also increase linearly. S decrease, Y also decrease linearly, right? So that means we can draw a graph like this. Okay, S and Y actually is a straight line. Okay, we have the red line is the data we collect, the real one, and the red one, the red line, is the data that, sorry, is a prediction we have for the X and Y. And since this is a straight line, okay, they increase linearly, we can write a linear equation in the form of y equal to ms plus c, straight line equation that that can be used to present this model. Okay, let me write here maybe. Okay, it's easier for me to, okay, say this is a straight line y equal to ms plus c. Okay, a linear equation that we can use to model, okay, the y as the revenue, and the, okay, and the s is the, what you call it, the spend, the cost of advertisement. Okay, so now, okay, let's look at here. Let's say we have this graph. Okay, this graph. Okay, this is the prediction, the straight line we mentioned just now. Okay, and this is the data we have. Okay, so assume that when we spend S1, we get Y1. We spend S2, we get Y2. And we spend S3, we get Y3. Okay, these are the real one. But for our model, okay, the model is not that accurate. Okay, so there is some error there. You see the error. Let me use red color. Okay, this is the error for the S1, sorry, S3. So here the recorded value is S3, Y3. You should get Y3, but in fact we just get Y3 prime. Let's say we call it Y3 prime. Okay, so the error is a E3. Okay, E3 is the error associated to S3, which is equal to Y3 minus Y3 prime. Okay, for S2 similarly, the value of E2, okay, the error associated to S2 is here. Okay, the value we get is Y 2. Okay, wait, I mean is the Y2 is I should write here. Okay, minus this one, the Y2 prime. Okay, correct not, the error of 2, and then the E1, the error associated with S1 is here, Y1 minus Y1 prime. Okay, this is Y1 prime. This is the E1, E2. Okay, so you see, the blue one, the blue straight line, is the model we use to predict this advertisement spending and the revenue, the relation between them. Okay, and the dots here, the red dots here, is the real data we collect. And obviously there's some error between the real one and the predicted one. So what's the total error? What's the total error we have for this model? You see, the total error, of course, it's very simple. E1 plus E2 plus E3, right? This is the total error. Okay, but wait, you see, one issue here. Y3 minus Y3 prime. This is Y3, Y3 prime. This is positive. Positive, right? And for E2, you see, this is Y2 is less than Y2 prime. So this, you get a negative. And E1, this is positive as well. Right? Y1 is greater than Y1 prime. It's positive as well. Okay, for this case, when we have error positive and error negative, you sum up, you should get some error. But it is possible that let's say if E2 is very small, I mean it's very large, okay, I mean here, if let's say the points here, it's possible that, okay, this one plus this one plus this one, the total error is equal to 0, right? But this is not true. This is not true because we have positive error, negative error, positive error. We sum up, we get a 0 error or small error. Is quite likely to happen. It is quite likely to happen. So we cannot compute the error in this form. Okay, because there are some positive, some negative. Okay, we cannot compute error in this form. But what should we do is we compute the square of the errors. When we make it square, all the errors become positive. All the errors become positive, then we should get a result which is more able to reflect the real situation, how large is the error is. So to make it square, okay, okay. So this one will get all the positive errors only, right? All become positive. So when all become positive, okay, we can measure the errors in a more accurate way. So the total error we have, is equal to this one plus this one plus this one. Okay, so this is the total error. Okay, but you see, when the data become larger and larger, I mean the size of data, we have more data. When we have more data, the error become larger and larger because all these are positive or 0, right? Become larger and larger. So it's not fair to the situation when we have more data, right? So a better way of measuring data is not the total error, but what is it? Okay, we call it as mean square error. Okay, we call it as mean square error. What I mean here is we find this one, okay, plus this one, the sum of them, okay, divide by 3. The mean square error okay, from name you can see. Okay, it means that we square the error first and then we find the mean of it. We divide by the total error, the number of the number of data we have. So you divide by 3. So this is so-called mean square error. So or in short, the mean square error, you can present it with one equation, which is, okay, MSE, mean square error, equal to 1 over n. Okay, n is the number of data we have. In this case, it's 3, and then sum of, okay, all data from what first until the end, the yi minus yi prime square. This is the error. Okay, the error of each one, square it, you sum it, you divide by the number of data we have. So this is so-called the mean square error. Okay, now with this mean square error, okay, if we want to optimize our model. We want to optimize our model. Here comes the numerical optimization, right? Optimize. Okay, if we want to optimize the model, that means we want to, when we face this line, this blue line, y equal to ms plus c, we want to find the best value of m and also the intersection, the c. Okay, we want to find the best m and best c to make this straight line, okay, get a smallest error for all the I mean not no we to find the smallest error, okay, I should say to find the smallest mean square error for the whole system. Okay, not for one data only, one point only, but in total for the whole system. Okay, you find the smallest mean square error. You want to make this one, the MSC, the mean square error, become the smallest. So here, let me write in the new page the mean square error, okay, which is equal to this one, 1 over n y. Okay, we want to make this become smallest. Okay, so how to do it? Okay, before we go into detail, this one, the yi prime, which is the value that we predict. Okay, we predict, you see on the straight line, actually is equal to the y prime. Okay, actually it's the ms plus c, right? Here, yeah, I should write prime here. Okay, so the predicted one. So okay, instead of writing this one, okay, this is not common, we use m and c here, but in machining sometimes we write this form, y prime equal to beta 0 x plus beta 1. Okay, just a change of the name only. Okay, m is the beta 0, c is the beta 1. Okay, if you want to use this beta 1, beta 0 also can, no problems. Okay, just different names only. Okay, so if this is the case, then what we have here is our mean square error can be rewritten in this form. Beta 0 x plus beta 1 square. Okay, so this is the equation that we want to minimize. Because we want to have smallest error. The total error is the smallest one. So we want to minimize. This is so-called the objective function or cost function. This is the cost function. Okay, so we numerical optimizations come in here, okay, to help us to find the smallest set of beta 0 and beta 1. Okay, but how to find this smallest value of beta 0 and beta 1? Okay, 1 minute, let me copy this one to the other page. 1 minute, yeah. Where's the to do copy? Okay, you see, let's say, okay, this is a function. Okay, this function. Let's say we call this function as j. Okay, j is a common variable we use to represent cost function. Sometimes we use L, sometimes we use J, same. Okay, and J here you see, J, okay, is a function in this form. Okay, and to make this function smallest, we want to find. 1 minute, let me. Okay, to to make this function smallest, or to make to find the best model, we want this function to be smallest. So we want to find the mean of j, this function to be mean. Okay, so the question here is, what is the variable that involved in this function? What's the variable? X and y? No, actually not x and y, but the one changing we can change is beta 0 and beta 1. Okay, for the object functions, yes, we have everything. Okay, we don't know y, we don't know s. Okay, we can put in s and y, okay, to compute some value. Yes, correct. But when we come to the process of optimization, we want to find the best set of parameters. The parameters that we want to find is not s and y, because s and y actually are the real data that given to us. But we want to find the beta 0 and beta 1, which is the one that we can change to get a better model. So we want to find, okay, the j, which is a function of beta 0 and beta 1, okay, in order to get the minimum value, okay, across all the beta 0 and beta 1. Okay, the writing like this means that we want to find the minimum, okay, of j, okay, with the change of beta 0 and beta 1. Okay, so to do this, how are we going to do it? Okay, to help you to understand the problem, okay, I draw again the graph. This is the point, the 3 red points just now. Let's say if we have only 3 points lah, okay. So what we want to do, okay, is what we can do is we can change the line. If this line, this model, wait, let me write y equal to y prime equal to beta 0 s plus beta 1. Okay, this is the line. Okay, so if this value or this line, okay, with this beta 1 and beta 0 doesn't give us a good one, we change the line. We change the line to maybe to change to this one. Okay, if this one not good enough, we change again, right? We change again to maybe this one. Okay, but of course we don't try an error like this. Okay, we don't try an error like this, but we use a more systematical way. The so-called more systematical way is we start from here. Okay, let's say we start from here. If we find that this is not good enough, okay, what we do is we change the beta 0, okay, to another beta 0. If this is a beta 0, okay, the first copy, the first value, and then we go to the second value. Beta 1, same thing, the first value is not good enough, we find the second value. Okay, and from the second beta 0 and second beta 1, we will, okay, try to find the third one if we can improve. Okay, so we keep on doing this. We keep on changing the beta 0 and beta 1, okay, in a systematic way to find the error. To find the value of cost function. Okay, and in each iteration, from here to here and from here to here, we will see the value becomes smaller and smaller. So how is this process being done? How is this process happen? Okay, this is what we are going to learn in the numerical optimization. In short, okay, it is some algorithm like this. It's a process like this. Okay, so first we have beta 0. Okay, beta 0, and for beta 0, which is not good enough, the first copy of beta 0, okay, the first value of beta 0, and we will, okay, minus it with a derivative of the objective function j. Okay, we minus it with the objective function j, which is a function of beta 0 and beta 1, over, okay, derivative of the beta 0. Why? Because this is about beta 0. Okay, minus this one, okay, and multiply with a small value called alpha, or sometimes we call it as a if you have learned the machine learning, you know this term, right? We call it as a learning rate. Okay, and after this process, you get a new beta 0. We call it beta 0, the second version, or the second value. Okay, the updated value. Okay, this is for the beta 0, and for beta 1, same thing. Beta 1, okay, the initial one, sorry, 1, okay, the initial first one, minus, okay, you derive the j objective function, okay, derive over the beta 1, okay, and then the value of this derivative you multiply with the learning rate as well. Okay, okay, and then with this one you get a beta 1, a new copy, new version. Okay, so we repeat doing this and this, okay, again and again and again. Okay, and then eventually we'll find, okay, what I mean here, this line will adjust. Okay, maybe start from here, then followed by this one, and then maybe after that this one, and so on. Eventually you get a best value, I mean best value of beta 0 and beta 1 to fulfill, to get the smallest value of j. So this is a process. Okay, this is the whole process of machine learning, which we call it as a linear regression, and with gradient descent. This is what we are going to learn. Okay, but one thing is learning rate is a term which is popular in machine learning, but here we call it as a step length. Okay, step length, because for every step, okay, you must compute a value, okay, which determine how far you want to move. This is so-called a step length. Okay, don't worry. If you are not quite sure about what we are doing here, especially, we will learn, okay, in more detail in the coming classes. So don't worry. So I just want to give you an impression. Okay, what we are going to do in the future is something about this one. Okay, so I think that's all for today. So okay, thank you.